technologies for around 30 years. And I also run a company called Orcro, which specializes in open source software compliance. So today I'm going to be talking a little bit about open hardware, open source hardware. The terms are sort of largely interchangeable. But to give you a little bit of background, typically we're talking about licensing a design, and that design will be licensed under terms that, if you're involved with open technologies, open source, free software at all, will be very familiar to you. So the license must allow making that design, modifying the design, and redistributing the design with or without modifications. None of that will come as a surprise at all. And there's an organization called the Open Source Hardware Association. They have a definition, and that preamble, which is on the screen there, looks very similar to the definition of free software. So just to put things in context, what are we talking about when we're talking about open hardware? Typically people tend to think about electronics. They can also be thinking about silicon chips, but they can be thinking about more physical things like cases, racks, and furniture. Typically mechanical devices can also be considered as being open hardware. So I've been involved in projects involving open source hardware, cars, boats, for example. All of these are items that can be released under open hardware licenses. And also 3D artistic works as well. So they don't need to be functional. They can be purely aesthetic. I put 3D printed works in there because people often think about 3D printed works as being a typical classical form of open hardware. And interestingly enough, fluids can also be open hardware as well. So for example, if you are releasing an engine, a car engine, something like that, it's going to need oil. Maybe you'll have a special formulation of the oil that it requires. And that can also be open hardware as well. Now, we have a number of intellectual property challenges when it comes to licensing open hardware. Now, I mean, typically, we'd be looking at copyright, and in that case, that's something that people will be very familiar with in terms of open source software. Patents tend to impinge more on hardware than they do in software. In many jurisdictions, it's not possible to patent software as such. So patents tend to impinge more often on hardware than they do on software. There are any number of different sorts of design rights in different jurisdictions, which can also apply. There are strange individual sorts of intellectual property, like plant breeders' rights in some jurisdictions as well. There's also semiconductor topography or mask rights, and which are more likely to be the sort of thing that is covered by open hardware licensing. There's database rights as well. So there's a whole plethora of different sorts of intellectual property rights which can be covered, which can apply to open hardware. And broadly, there are two types of open hardware license, analogously with open source software. So there are permissive licenses that essentially allow you to do anything that you like with the design. And then there's reciprocal or copyleft licenses that require you to make the design documents or the modified design documents available as well. So again, if you're familiar with open source software, you'll be very familiar with this as a concept. So the sort of challenges that we have when we are trying to come up with an open hardware license is that you will find that there is a more complex mix of intellectual property involved in open hardware than there is in open source software. So all of these aspects need to be considered in the license. One of the less understood situations, as far as software is concerned, there are many, many chances to allow the license obligations to impinge. So essentially, every time you make use of that software, every time you transfer it, if you're going to be downloading it, installing it, running, etc., copies of the software are going to be made. And every time a copy is made, it's going to require a license for that particular use case. And whenever a license is required, then it means that the conditions that apply to that license will also apply as well. With hardware, that's not necessarily the case. The intellectual property obligations are not going to impinge as often. I mean, for example, if you make a 3D printed hammer, you don't need to rely on any form of license every single time you use that hammer. And the sort of conditions that we're talking about, again, analogously with open source software, are for permissive licenses. You're looking at things like attributions, license texts, etc. And then for reciprocal share alike or copyleft type licenses, you'll also be looking at making the source code available as well under the same license. So just to give you a brief idea of the sort of spectrum of open hardware licenses that are out there, a lot of people just use open source software licenses. That comes with its own sort of particular problems, but you'll frequently see open hardware licensed under BSD, MIT, Apache, and some new license called the GPL, which I think is supposed to say GPL. And quite frequently you'll see the designs also licensed under content licenses, which are typically more appropriate for content, such as the Creative Commons suite of licenses. And then there are a number of licenses that have been drafted specifically for use with open hardware. CERN Open Hardware License, the SolderPad hardware license, TAPA, the Open Compute project licenses, which I would have a sort of slight query as to whether they count as open or not, but that's probably not something to discuss today. And most recently, the Open Atom Foundation in China has just released the Open Atom Open Hardware License, which is a permissive style of license. So this raises a number of questions that you need to bear in mind when you are drafting an open hardware license. So what level of detail do you actually need in the design? Now, one way of thinking about this little sort of tool for thinking is to think about what is software made of. Well, software is essentially made from a pile of zeros and ones. What you're doing is you are coming up with a recipe for combining those zeros and ones in a particular order, and you will end up with a piece of software. Hardware is different. Hardware is made of atoms. Atoms are not quite so predictable. So when you're compiling software, you are going to get this relatively predictable string of zeros and ones. I like to say that software compilation is deterministic. Computer scientists will tell me that it's not, because there are plenty of variables depending on the compilation environment. But let's assume, for the sake of argument, that it is. And certainly, it's possible to come up with mechanisms that allow builds to be reproducible in certain ways. So same output means that same input means that you have the same output in each case. That's not necessarily the case with hardware, because you are not getting a set of instructions that will enable you to make your piece of hardware out of a pile of atoms. You're necessarily going to have some level of abstraction that is higher than that. And you will necessarily be looking at components there. So for electronic circuits, if you're looking for a design of an electronic circuit, that design will be made out of components. It'll be made out of resistors, capacitors, inductors, transistors, and so on, as well as the printed circuit board that they are connected to. One thing that I'd like you to think about is just moving to a different realm of openness now. If we're thinking about things like open government data and open source artificial intelligence, then they are also essentially made of components as well. The training data can be regarded as a component as far as AI is concerned. If you're looking at government data, then even though that may be available under an open license, what you're getting is you're getting a bunch of statistics which you are able to use and reproduce and so on under that license. But what you will not be getting is the fundamental data that created those statistics in the first place, the outputs from the censuses or the surveys or whatever the government has undertaken to provide that information. So this question of how to deal with components in open licensing, it is not a new one. It's been considered in other fields such as open data licensing and open artificial intelligence. So just looking at the question of components, if you have a design of something that contains components, do you also need the instructions to make the components individually? So we're looking at a sort of hierarchical structure here, where you have a design contains the components. If that design is to be regarded as open, do you need the instructions for how to make each one of those components? If you don't have those, can you truly describe the design as open? And when we drafted the CERN Open Hardware License, we came up with a concept of available components. And if a component is available, that means that either you do have all the instructions to enable you to make it, or alternatively, you have information about where to source that component and all of the specifications that you will need in order to make use of that component in that particular design. Now, just briefly looking at the Open Source Hardware Association definition. As well as talking about licensing, and clearly the design would have to be made available under an open license, it also has to fulfill some additional criteria. First of all, the design has to be made public itself. You know, that seems relatively obvious, but at least that's explicitly stated in the Open Source Hardware Association definition. But the definition also states that the interfaces to software must be made public, or the software must be released under an OSI approved license. And if you have a hardware design and you want it to be certified by the Open Source Hardware Association, they have a certification program, then some additional requirements are that you must use open components wherever possible. So that's not an absolute requirement, but it's a wherever possible requirement. So this demonstrates that these are requirements that are over and above the simple requirement that the design itself has to be made available under this license. So let's look at some issues with openness as far as sharing and facilitating reuse are concerned in licensing. So I'm going to quickly cover a few topics here. I'm going to compare the open source hardware development process with the open source software development process. And then we're going to look at whether that process varies depending on the type of hardware that we're talking about. Because some hardware projects are very much more like software in the way that they're designed, developed, tested, implemented, and so on. I'm going to very briefly look at some economic arguments that will distinguish between open hardware and open source software, particularly as far as copyleft is concerned. And then I'm going to look at some issues that are specific to permissible copyleft licenses in particular. So let's ask ourselves the question, why is open source software so successful? And we've very much focused on the licensing model. And the licensing model is undoubtedly an extremely important factor here, but it is not the only factor in the success of open source software. One of the factors is the development environment is free or low cost, and it's very easily available. And for a typical piece of software development, you can actually do that development on some pretty low cost hardware as well. Much of the software and tooling that you need is going to be free or low cost. So, you know, you can use Linux as your operating system. Your development tools like GCC, also free and low cost. And critically, the platforms that you will be using in order to collaborate and track that development are also easily available and accessible, and in many cases they're free for open source projects as well. So if you look at GitHub and GitLab as classic examples of that. And then of course, in order to make use of those platforms, you're going to need internet bandwidth, and that is now available at reasonable cost to most people in most parts of the world. So that creates a virtuous circle of easy community development, and it means that many developers are potentially available to help and to create a community of development. And that community can be very broad, I mean, potentially worldwide. So how do we contrast that with hardware? Well, It can require expensive proprietary development software. So if you think about sort of CAD/CAM systems, for example, those can be extremely expensive. In order to make hardware, the harder sorts of hardware, you're going to need complex and expensive physical tools, things like lathes and milling machines, 3D printers. In order to ship hardware, they're physical items, so there's shipping and transport to consider. You may need a particular amount of space and environment in order to create that, and maybe environmental constraints. So, if you're making silicon chips, as an extreme example, you're going to need an extremely clean facility. It's going to have to be temperature and pressure controlled, humidity controlled, and so on. And then, of course, you'll be thinking about the cost and the quality of the feedstock and the components that you're using, the raw materials that you're using to create that hardware. So let's have a look at the design, build, test cycle. So this is applicable to software and hardware. So you basically start with a design, then you will build that design as part of the build process, then you'll test it, and then you'll go around that cycle, round and round and round, until you feel that you're in a position to make the product available, and then you'll go to the productize section, and the customer gets access to it. This can be as simple as just making the code available for download somewhere, or in the case of something physical, it can be significantly more complex than that. But then that will always go back to the test cycle, and that will go round and round and round. And the distinction between hardware and software is that whether these activities are happening in the physical domain or whether they're happening in the digital domain. Because with software, if everything's happening in the digital domain, this is a lot more effective, it's a lot quicker, it enables collaboration much more effectively. If it's happening in the physical domain, then the build, test, design cycle will slow down significantly. Collaboration becomes much more difficult. Now, this can be short-circuited to a degree by adding simulate in there as well, and this happens a lot in terms of hardware. Car manufacturers have a lot of extremely expensive software that will enable them to simulate various designs, and that will certainly reduce the cost. But again, it's expensive software. It's not necessarily accessible to individuals. So this is something that creates another difference between hardware and software. So let's look at one particular sort of open source hardware development, which is the FPGA, the field programmable gate array. So if you're not familiar with an FPGA, it is a silicon chip that enables itself to be, you can configure it in order to essentially become any other sort of chip. It can become a processor, it can become a piece of memory, it can become some form of interface or whatever. And to do that, you write a formal description of the logic in a form of hardware description language, and then you use that logic description to create a bit stream, and that bit stream is literally just a sequence of zeros and ones, which you then apply to the FPGA, and once that FPGA has been configured using that bit stream, it becomes whatever you want it to be, whatever you've designed it to be, the memory chip, the interface, the UART, whatever that happens to be. Now, with software, obviously you write code in a programming language, and then you compile it to create object code, and you can run that on a computer. This is very similar. The process is very similar, and in fact, a hardware description language looks very much like a software programming language. And actually, if you speak to HDL developers, they'll often talk about the code they're creating as code, and they will talk about, rather than configuring the FPGA, as configuration. So it's a lot like software development. So HDL development has a lot in common with software development. And from that perspective, a lot of the dynamics that apply to open hardware development, if we're talking about HDL development, they are very similar to the dynamics that apply to software as well. Right, I'm not going to go into this in detail now, but there are issues with enabling reciprocity and copyleft to apply to open hardware because, as I mentioned before, there's less opportunity for these obligations to apply with open hardware than there is with open source software. There's also a problem with copyleft in that it's difficult to figure out where the boundary for the copyleft should lie. So if you have one component that is in your piece of open hardware that is subject to a copyleft license, does that mean that, for example, the whole of whatever that design is that contains that single copyleft component also has to be released under the same license? So this is something that can be quite difficult to deal with. And an economic argument is that around reverse engineering. It's often a lot easier and cheaper to reverse engineer and to recreate something in the hardware world than it is in the software world. So I shall skip this one. This is the economic issue here, is that basically with software it costs close to zero to make a copy of even incredibly complex software. It's just a question of copying the bits. With hardware, it's much more difficult. So if you're going through that process anyway with hardware, then you're already committed to a large amount of expense. Essentially, it's fairly easy to avoid copyleft licensing of hardware because reverse engineering and essentially creating a sort of clean room mechanism for redesigning the hardware is significantly more straightforward than with hardware than it is with software. That's an oversimplification, but it's one of the pointers as to why copyleft license may not work. So what we're looking at here is a sort of form of hardware in the spectrum. Essentially, a lot of the criteria that apply to open source software, and the reason why it's so successful, I maintain, are much more likely to apply to open hardware if that open hardware has software-like development characteristics, such as with an FPGA. I call it a hardware in a spectrum. I think it's a dreadful piece of terminology, so if you can think of something better, please let me know. I was involved in the European Commission impact study on the competitors of hardware a few years ago, open source software and hardware, but I was leading the hardware side of things. We do go into some of this analysis here. There's a link on the screen there, and I'll share the slides. But if you want to see some of this analysis in greater depth, that's there. And we took some of this thinking into the CERN OHL. So what can open hardware learn from open source software? Well, there's an example of many of the activities that are very successful in open source software that can also apply to open hardware. And again, I'm not going to go through those individually. So in summary, open hardware is more challenging than software, but you've got to be aware that the community and development dynamics may well be very different, and do not assume that other opens will work like open source software. We have some advantages in open hardware. There's less license proliferation, but beware that copyleft and reciprocity may not work as well for open hardware. But none of that means that open source software and open hardware aren't fields that can learn from each other. Right, thank you very much indeed. Thank you. I don't know if we've got time for any questions.
Okay, thank you for that overview. So you mentioned that it's difficult to determine where the boundaries are specifically with regards to reciprocity.
Yeah.
Why is that difficult? Like, it seems to me, like, intuitively. So if you have a piece of hardware, like a circuit that is licensed, let's say, certain hardware copyleft.
Yeah.
And you use that piece of circuit is reused in a larger schematic.
Yes.
That to me means that the entire thing should be copyleft. But
okay, so I mean, if you have a resistor that's copyleft, then any license that any hardware that contains that resistor is therefore going to have to be released under that copyleft license. And then when and let's say that a resistor goes onto motherboard, as soon as you put the motherboard into a case, does that case then have to be released under the open hardware license? And then when you put that case into a rack, does the rack have to be released under the open hardware license? So I think this is the issue that we have is, where does it stop? What is a component? And
this is similar to like with software where you have if you put a piece of GPL software in a proprietary operating system.
Yes.
It doesn't mean the entire operating system is GPL.
Well, it might. And this is something that we spent a lot of time sort of analysing and looking at. Certainly, that's not the case if it's LGPL. With GPL, it'll depend on the interaction between that piece of GPL code and everything else. And this is something that's fairly well understood, and still not completely understood, but fairly well understood as far as software is concerned. But in my view, it's not quite so clear-cut in hardware. And I think it's also, in a way, becoming less clear-cut in software as well, because when you're looking at technologies like containerization, for example, that tends to make it quite a lot more difficult to analyze exactly where these boundaries lie. Yeah,
Thank you.
Thank you for the question.
How about opinion about data sheets?
Data sheets. So I think data sheets are critical. I mean, certainly thinking from a sort of open, a certain open hardware license perspective, in order for a component to be considered to be an available component, it will have to come with a data sheet, and that data sheet will have to provide all of the information that's necessary to make use of that particular component. And it's sort of obvious things like if it's a resistor, the capacity, the power capacity of the resistor, the resistance, but also things like the physical size and shape of it. And it could also, in certain cases, also require certain sort of tests and calibration suites and so on that come with it as well. So what's specifically required in the data sheet is actually going to depend on what the ultimate use is, what the use case for that particular component is going to be.
Hello. Thank you very much. Well, I have a question about patents and this licensing.
Yeah.
Yeah, I have some, for example, some piece of hardware, and I patent.
Yeah.
This patent is basically, let's say, restriction on others to fabricate my device in exchange of making the design public, right?
Yes. Yes.
So once I have that, for example, then I kind of like open license it with these licenses, and that will allow people to fabricate my device.
Yeah.
So far, so good.
Yeah.
But for example, if I have a device that for some reason cannot be patented, then does it make sense that I open license it? No?
So you're.
You get the question, right?
Yeah, exactly. So what you've just described is the way that the TAPA open hardware license works, or doesn't, as the case may be, which sort of makes the assumption that all hardware might be patentable or not, and its obligations rely on the fact that it might be patentable. But of course, I mean, there are plenty of other intellectual property rights that will apply in a design that are not necessarily patents, which can still be licensed and can still be used to apply conditions. So copyright is the obvious one, but it could also be database right in a list of all the components, for example. So from that perspective, there's not a huge amount of difference between open source software and open hardware, but there's probably less focus on copyright in open hardware than there is in open source software.
In the case of hardware, the copyright in the physical thing doesn't apply, right? Because copyright applies to intellectual property rather than.
Yeah, I mean, this is yes, that's a good question, and this is something that varies a lot from jurisdiction to jurisdiction. So some jurisdictions will say the copyright only applies to the design itself, and as soon as you turn that into the hardware, then the copyright becomes irrelevant. And in that case, you know, there's not going to be any restriction on somebody taking just the hardware, reversing reverse engineering that piece of hardware and then replicating it. In other jurisdictions, you will find that the intellectual property, the copyright, will carry on into the design. So, you know, an example of that would be a circuit board layout, which is, you know, certainly under English law is regarded as being an artistic work, and it's still an artistic work when you take it from the design phase and put it onto a circuit, you know, that's etched in copper. So that will vary a lot from one jurisdiction to another.
Okay. Yeah. For example, like for patent, it's something you define, maybe some lawyers could be. Yeah, but if I don't have it and I just have my piece of software,
yeah,
and open license, would that somehow protect my design if someone wants to patent my design?
Yeah, again, this varies a lot from jurisdiction to jurisdiction and also from the type of intellectual property. So copyright happens automatically and you don't need to register that, although you can in some jurisdictions get advantages by doing that. Patents will always need to be registered and they're very expensive to do that. As a hybrid, there are forms of design rights. Some of them happen automatically, some of them don't. So you know, database rights in the European Union happens automatically. It varies a lot from the type of intellectual property and also from the jurisdiction that you're looking at as well. Yeah.
Thank you. Thank you.
Yeah.
Do we have any more questions? Then I think there's a short break. There's some seconds that we'll take it and we'll resume it in the next half hour.
Right. Thank you very much, everyone.
Presentations, by the way.